to know the planet, to know the universe, to find out what makes things work and why things are the way they are through observation, study, and experimentation. We can unleash the power of the universe and make almost anything happen. This is Understanding Science.
From large cold clouds of gas and dust, small particles begin to clump together. Their own gravity and pressure from nearby stars cause the small masses to form a large single mass. The forces continue pulling the small gas and dust particles together, forming a larger and larger ball. The particles are moving so fast that the proton's natural electrical force is overcome by the tremendous speed of the atoms, and they begin colliding and attaching to one another, forming helium. During this process, the matter, because of its tremendous speed, becomes energy. And voila, a star is born. So, what is energy? Can matter really be changed into energy? And how does energy travel? Hi, I'm Dr. Science, and we're just about to find out. Energy is the ability to do work. Anything that moves has had energy applied to it. So, energy is the ability to cause a change. Notice I said cause a change, because if energy is stored in an object, it has potential energy. Huh? The energy stored in an object due to its position is potential energy. Does this ball have potential energy? Well, is the ball in a position to move? If I let the ball go, will it move? Yes. So because I'm holding it in this position, the ball has potential to move, or potential energy. Now, I dropped the ball and it fell. It moved. A moving object has energy to make it move, called kinetic energy. So, kinetic energy is the energy that a moving object has due to its motion. Quite simply, this is potential energy, and this is kinetic energy. There are 5 types of this energy. Mechanical energy is any energy associated with motion. If it moves, it has mechanical energy. Now, heat energy is the internal motion of particles of matter. The faster the particles in matter move, the more heat energy they have. Rub your hands together. What do you feel? They begin to warm up, right? You know what we've done? We've just converted mechanical energy, the rubbing of our hands, into heat energy as the particles in our hands move faster. So, heat energy often causes a change in temperature. And when something cools down, heat energy is being lost. Let's rub our hands together again. They get warm, right? When you stop rubbing, your hands cool off as they lose their heat energy, right? Now, next is chemical energy, the force which bonds or holds atoms together. Like our story at the beginning, stars are formed by chemical energy. Electromagnetic energy is the moving of electrical charges. At last, nuclear energy. This energy is created by breaking up the protons that have bonded together, providing a tremendous source of energy from an atom's nucleus. Now, let's do a little experiment to find out more about heat energy. Heat is the motion of particles. The faster they move, like when you rub your hands together, the more heat energy is being used. Yeah, right. Cold is the absence of heat. Take an ice cube and place it in a beaker. Now, wait a minute and look at the ice cube as it begins to melt. What is happening here? Heat from the surrounding air in the beaker is being transferred to the ice cube. So, the ice cube is absorbing heat. The moving of heat from one object to another is called heat transfer. Heat moves from one substance to another in three different ways: conduction, convection, and radiation. Conduction is the transfer of heat through a substance or by contact of molecules. Now let's take a look at the beaker with ice in it and figure out what's happening as the faster moving warm molecules in the air are colliding with the colder molecules of the ice. Heat is being transferred. Heat transfers from warmer molecules to cooler molecules. This conduction or contact of molecules melts the ice cube. Now let's find out what substances make the best conductors. Here we have a wooden spoon, a metal spoon, a glass rod, and a plastic spoon. On the burner, we have a beaker of boiling water. Now, if I were to place the wooden spoon in the beaker, do you think it would get hot? Since we're on video, you can't touch the object, so you'll just have to trust me. First, I'll touch the wooden spoon. No, it's not hot. Do you think the plastic one will be hot? No, it's not hot either. Let's try the metal spoon. If you think it's hot, you're right, it is. Now what about the glass rod? You see, some objects get hot and some don't. The substances that conduct heat better than others are called conductors. Most metals are good conductors of heat, like copper, used in plumbing to keep the water in hot water pipes heated. Copper is also used in the bottoms of cookware to conduct heat for cooking. Most pans have plastic or wooden handles because those substances don't conduct heat easily. Wood, plastic, and glass are what we call insulators. Because they don't conduct heat, wood makes an excellent construction material in buildings, and fiberglass is often used in insulation in attics and walls. Heat is also transferred through convection. This takes place in liquids and in gases as molecules move in currents. Convection is how heat energy is transferred in many homes. As molecules near the heat source heat up, they speed up and start to spread out in currents. The warmer particles become less dense and rise, and the cool particles fall. The air moves around the room in currents. Earth heats up in the same way. Air near the surface heats up and rises, then cools and falls to the surface again. And these currents of air contribute to the planet's weather. When you see birds soaring upwards, they are riding the upcurrents of warm air. Heat is also transferred through radiation, and this is how heat is transferred through space. Radiation can travel as invisible light, known as infrared rays. Radiation is also the heat you feel coming off of a hot stove or the heat surrounding a fire. I have a tasty experiment to demonstrate with heat radiation. Put a marshmallow on a stick and place it above the flame. Now, even though the flame doesn't touch the marshmallow, the heat radiated by the flame toasts the snack. Now, we know that heat energy is the moving of molecules. So what is temperature? Temperature is the measure of the average kinetic energy of molecules. In the boiling water, the molecules are moving, some faster than others. So, temperature measures the average of those moving molecules. Moving molecules are kinetic. The average kinetic energy of water is measured by a temperature reading. Energy has its own unique way of traveling. A disturbance that travels through space or matter is a wave. This wave is energy moving from one place to another. As a wave travels through a substance or medium, it doesn't move the particles of matter with it. Only the energy that produces the wave moves the wave. You can see how waves of energy travel with this simple experiment. Take a pan with some water in it. Drip a drop of water into the pan. Do you see ripples moving away from the drop of water? These ripples are the energy traveling through the water. Since it's moving, the water dropping has kinetic energy. The kinetic energy is then transferred to the water and travels through the water as a wave. Remember I said that a wave is just energy traveling through a medium. It doesn't move the material it is traveling through. We can prove this by a simple demonstration. Just place a cork in the water and drop another drop of water into the pan. Now watch closely. As the waves move away from the center, they pass under the cork. The cork is still where it was. When you go to the beach or a wave pool, a wave comes in and you bob up and down. It doesn't carry you forward. Surfers try to catch the energy as it passes under them and ride the wave in. We're going to find out more about characteristics of waves. This is important in understanding how light behaves, which is our next lesson in energy. The parts of a wave are crest, trough, wavelength, frequency, and amplitude. The crest is the highest point of the wave. The trough is the lowest point. The frequency is the number of complete waves that pass a point in a certain amount of time. The unit used to measure frequency is called a hertz. A frequency of 1 hertz is equal to the wave or cycle per second. This will be important in a minute or two. 1 hertz is equal to 1 wave per second. We know a wave is a disturbance in a medium or matter. The amount of this energy is called the amplitude of a wave. The amplitude is the distance that molecules are displaced from their resting position. The more energy a wave has, the more amplitude it has. Wavelength is the distance between 2 troughs or 2 crests and is usually measured in meters or centimeters. Back in our wave pan, let's drip a drop of water in the center. We know the wave moves away from the center. Now, look at what happens when the wave hits the side of the pan. It bounces back. The bouncing back of waves is called reflection. After a wave strikes a boundary that doesn't absorb its energy, it bounces back, or it's reflected. The incoming wave is called an incident wave, or ray. The angle or direction of the incoming or incident wave is called the angle of incidence. The wave that is bounced back is called the reflected wave. The angle of the reflected ray or wave bouncing back is called the angle of reflection. The law of reflection states that the angle of incidence, or incoming, is equal to the angle of reflection, or outgoing. We can show this by using a mirror and placing it upright. Fold a piece of paper lengthwise and draw a line down the center. Then place it in front of the mirror. With a ruler, draw a line at an angle toward the center of the line. In the mirror, we see the line of incidence, or the incoming line. We also see the line of reflection going out in the opposite direction. Now, very carefully, draw the reflected line into our paper. Using a protractor, we measure the lines. The first line we drew, our angle of incidence, was at a 45-degree angle. The second line, or line of reflection, was also at a 45-degree angle. The angles are equal. When light is reflected, the type of surface will determine the kind of reflection that is formed. But no matter what kind of surface it hits, the angle of incidence is equal to the angle of reflection. Let's take a look in the mirror. You can see your reflection in the mirror, but not on a wall. Why? In both cases, the angle of incidence is equal to the angle of reflection. But you can't see your reflection on a wall. So what's the difference? Well, the mirror is very smooth. The waves coming in will hit the smooth surface and bounce back in a straight line. The wall, on the other hand, is not smooth. Its surface is very irregular, and the waves coming back are bouncing back in all directions, so you don't get a reflected image. The light that is scattered in all directions due to an irregular surface is called diffused reflections. A diffused reflection may not be desirable for seeing our image, but it is important for some things. Imagine if the sun's rays were not diffused as they enter the Earth's atmosphere. If the light rays didn't scatter off uneven surfaces and dust particles in the air, you would only see objects that are in direct line with the sun's rays. You wouldn't be able to see the sides and edges of objects. Waves travel in a straight line and don't bend as they travel through a medium. However, when a wave passes at an angle from one medium to another, like air to water or air to glass, then they do bend. They bend because the speed of the wave changes as it travels from one medium to another. This bending is called refraction, the bending of waves due to the change in speed. You've seen this one before. Place a pencil diagonally in a pan of water with part of it sticking out. When you look down at the pencil, it looks like it's split in two pieces. Well, that's because light bends or refracts. We can take our mirror outside and bend some light. If we place it so a beam of light hits it, we can bounce that light off the mirror and shine it on a wall. When we bend the light, we hold the mirror in one direction, but the refracted light is a different angle. This diagram shows how the incoming beam of light is hitting the mirror at different times and is bounced back at a different angle. So, energy moves from one place to another by waves. And now that you know a little bit about waves behave, we can now move on to another form of energy, electromagnetic. To understand electricity, we need to go into the makeup of atoms. Atoms are made up of subatomic particles, including protons, neutrons, and electrons. Protons and neutrons are found in the nucleus of the atom and have a positive electrical charge. Electrons occupy different energy levels outside the nucleus and have a negative electrical charge. Now, notice that the word electricity is related to the word electron. Neutrons are neutral and have no electrical charge. Electricity behaves according to this simple rule. Like charges repel each other, and unlike charges attract each other. So, if two positive charges face each other, they push each other away. And two unlike charges, such as a positively charged object and a negatively charged object, will pull each other together. Do you think a balloon is electrical? It's matter, and matter is made up of atoms. Atoms are made of positive and negative particles. In every atom in this balloon, there are the same number of negatively charged electrons as there are positively charged protons. Because the electrons are freer to move around than the protons are, we can change the balloon's charge by making the electrons pile up on it. Right now, there is no electrical charge in this balloon or on this cloth. But as I rub the balloon with the cloth, I'm transferring negative charges from the cloth to the balloon. Now, the balloon has more negative charges than the cloth, and we can prove it. The stream of water bends toward the balloon. If I hold it there long enough, the balloon will lose its negatively charged electrons and become neutral again. So, a neutral object can become electrically charged when it gains or loses electrons. This is electricity, defined as energy associated with electrons moving from one place to another. The electrons we moved to the balloon stay at rest, and this is static electricity. When electrical charges build up in a storm, they are static, and when they're released through electric discharge, we have lightning. When electrons move through a wire, it is called an electrical current. When we turn on the lights, we have provided a complete path for an electrical current to flow, or an electrical circuit. When we turn the switch off, we close the circuit. Amazingly, energy is in constant motion, changing form for our everyday use. Fossil fuels, which are stored chemical energy, are converted into heat in power plants, which eventually turn the turbines, making mechanical energy that is converted into electrical energy, so you and I can have electricity to run our hair dryers, which is heat energy. While energy can be converted or changed from one form to another, energy can neither be created nor destroyed. This is the law of conservation of energy. In 1905, Albert Einstein presented his famous theory of relativity, which relates this law to all matter. Matter, like energy, is neither lost nor gained. It just changes form. I'm Dr. Science. I'll be seeing you.
This program has been a presentation and production of TMW Sales Company. For information on other programs offered by the company, contact the phone numbers on the screen.